Hello, everyone. Thanks a lot for the introduction, Vicky. Hi. Today I want to talk about graph neural networks, and hopefully everyone has had a good lunch and not too sleepy after the lunch. I'll try to keep it brief. This is not to lose you. In terms of outline, I'll start off with the promising potential of graph neural networks, and then quickly after that, I'll go into the fundamentals of graphs, why graphs, and we'll discuss a little bit about why graph neural networks specifically, and then go into what the workflow of a graph neural network pipeline looks like, and briefly discuss some architectures and limitations and emerging trends. So graph neural networks have been quite popular in terms of keyword searches over the last 4 or 5 years. I believe it's the ICLR 2022 had graph neural networks rank in top 3 among the most searched keywords for that conference. And graph neural networks are special in a way because they've found their application in various fields, various different types of fields. I'm sure a lot of other machine learning algorithms do as well. But let's look at the resume of graph neural networks, which is quite exciting to me at least. I've personally been very excited about learning graph theory growing up in the universities, so this topic is quite special to me. So one of the things that worked out for graph neural networks early on was that there was this antibiotic called halicin that was discovered by scientists at MIT using graph neural networks, where graphs were used to model molecules and then classify those molecules as antibiotics. And halicin was a completely new type of drug that was discovered and then was found to be useful for specific types of bacterial strains that that we didn't have solutions for before. Graph neural networks also have a good bit of application in social network analysis, for example, in matchmaking. They can be applied to transportation networks. For example, there was a collaboration between Google's DeepMind. It was an internal collaboration, Google's DeepMind and Google Maps to use graph neural networks to improve the ETA prediction of Google Maps by roughly 50% in some cities around the world, like Berlin, Jakarta. And graph neural networks have also found their way into recommender systems, as you can see from engineering blogs online of Uber Eats, Pinterest, et cetera. If you want to learn more about that, I do recommend looking at how exactly these companies are using graph neural nets. But before we dive deeper into what graph neural networks are, I wanted to quickly touch on what graphs are to begin with. So graphs are a very versatile, a very flexible type of data structure, and that's one of the reasons I like them so much. Graphs essentially represent entities and their relationships, and that's pretty much it. In the graph theory nomenclature, you would use the entities you'd call the entities as nodes, and the edges as are basically what represent the relationships between those entities. If I were to take an example to illustrate what a graph is, one could look at a social network, and that's a very good example of a graph. So examples such as Facebook, Twitter are both good examples of graphs where nodes are basically human beings, people everywhere, users, and edges are relationships between them. And the basic type of graphs, there are 2 types of edges or relationships that you could have. One is an undirected edge, which is it's present in an undirected graph. It's similar to Facebook, where if person A is friends with person B is also friends with person A. So it's a bidirectional relationship. But then there is something like Twitter, where person A may be following person B, but person B may not follow back person A, and that's a unidirectional relationship. So these types of these types of networks can be abstracted into a graph, and the cool thing is these nodes don't just have to sit there on their own. They can have all kinds of features of their own. For example, each node can have a person's age, name, where they live, etc., right? So each of these nodes could actually be quite feature rich. So we did briefly discuss what graphs are, right? And they are a very generic data structure, and they basically model connections between entities. And so the truth is, there are several complex real-world systems that can be modeled as graphs, but they cannot necessarily be modeled as other things. If you can model them as other things, that's great. It's I think there's no necessity to overcomplicate it and represent them as graphs. But if you cannot, then sometimes there is just no alternative, because graphs are pretty much what you have in order to represent such type of data. And so briefly, from there, I would want to touch on why graph neural networks. So if you look at applying, let's say, machine learning or deep learning techniques on graphs, then there's a little bit of a challenge that one would face in the beginning, and that is traditional deep learning architectures are all good for Euclidean structured data. By that, what I mean is data that are tabular data, audio files, videos, images, and text, and these are all Euclidean structured data. What I mean by Euclidean structured data is data that can be represented on a plane surface and in a multi-dimensional planar surface. So anything that we generally imagine in an n-dimensional space, like a vector space or an n-dimensional coordinate system, they're all Euclidean spaces. Whereas such type of a space does not necessarily work for representing all types of data. For example, social networks, biological networks, transportation networks, and knowledge graphs are quite complicated, and they are not necessarily, they don't necessarily fit into the Euclidean in the Euclidean spaces. So we categorize them as non-Euclidean unstructured data that can only be modeled or represented by graphs, and that's really the crux of why graph neural networks are necessary. Now, to give you a little bit of a simpler example, I would say if you look at a Euclidean space, the difference would be, for example, if you take one point and another point, the shortest distance between those 2 points will always be a straight line. However, on a non-Euclidean space, or for example in a graph, that may not be, because for example, if there is the shortest distance from this node to this node would not be the straight line joining those, but going through these or potentially going through these other nodes. And that's sort of why it's more complicated to represent, and why it's harder to extrapolate to machine learning and deep learning algorithms. But to make things a little bit, I'm assuming, more, like at least for me, I was more familiar with, let's say, images and convolutional neural networks than I was on graph neural networks when I started to look at these. So there are many ways to kind of explain how graph neural networks work, but I would like to sort of take the route of convolutions to get there, and sort of also explain what some of the challenges are. So over here on the left side, you would see a typical, like a two-dimensional image grid that has pixels in it. And this is, if you have seen any convolutional neural network tutorials, you'd probably have seen something like this, which is a learnable kernel that takes a patch of this image, and it goes and swipes across this image one by one and computes this value over here, and then so on and so forth. But, and this is all possible because this is a very fixed two-dimensional grid, and this is also a two-dimensional grid. And you're able to take this, and you're able to swipe this across the image in patches. However, for a graph, that sort of thing does not really work, because first of all, there is no real structure to it. A particular node may have any number of neighbors as nodes that it's connected to. It may not be, it may not be fully, it may not be easily extrapolated to that, mainly because of those reasons. So you cannot necessarily take something of this sort and sort of swipe over a graph and intuitively be able to get any convolutions out of it. So with these challenges, what got introduced was this algorithm called message passing, which I'll be covering in this slide. So any questions so far? Thank you. It's either a good sign or a bad sign. Okay. So let's look at the graph neural network workflow. So message passing is kind of what makes graph neural networks work. And the workflow is basically the same. It's as expected. The input would be something that of a graph structure, which would be in a non-Euclidean space. And it will have the initial node features like we looked at, right? And then that would be fed into this graph neural network. And then there'll be some output that we will be using to run some predictions. And so for this to happen, there's a special type of convolution that was introduced, and which is called message passing. How that works is basically you're still aggregating information just like you're aggregating information in GNNs on images, except it's a very unstructured way of doing it. So perhaps we could look at this particular node and look at how it is exchanging messages with its neighboring nodes. These exchanges are done in iterations, and at the very beginning of the iterations, before anything is done, each node has its own special, has its own initial set of features, right? And then as one iteration happens, every node sort of imports a little bit of its information into all its neighboring nodes. So at the end of iteration 1, the value of the features would be a weighted combination of of its own values plus the messages that this node received from its neighboring nodes, which are these three. Now you can see that in the first iteration, sure, what this node would have at the end of it is an aggregation of its own values and its neighbors' values. However, at the end of the second iteration, though, you should note that much like this particular node got updated, this node also got updated with information from its neighbors. So the features of this particular node now have information about aggregate information of its neighboring nodes. And the next time that in iteration 2 that node passes its information to this node now has some access to information of these other nodes, which are 2 degrees apart from the first node that we were looking at. So this is how information is aggregated through and percolated throughout the network. And then and this is done for a fixed number of iterations, oftentimes a hyperparameter, and then passed through a few nonlinear layers, and which is where the feature transformation happens, and then it's output as a node embedding. Now, once the node embedding is done, that's when you're able to, let's say, that's when it is actually in a Euclidean space. It's not in a non-Euclidean space anymore. It's actually in a vector space, right? So you can apply any kind of regular machine learning algorithms on top of that. Certain popular ones for graph neural networks are link prediction, node classification, clustering, and graph classification. So in order to intuitively understand what GNNs do really, so what they actually do is they're basically an encoding mechanism. They take this highly complex, unstructured, non-Euclidean data structure, and then they encode it into some kind of an embedding space where a notion of similarity between nodes in the original graph is maintained in the embedding space as well. So that's really the crux of graph neural networks, and it makes machine learning models work with graphs. And there are three flavors of graph neural networks. I'll go over them briefly. There are more, but these are the more popular ones that you come across. There's graph convolutional networks. This is very similar to what we saw. Well, message passing is kind of integral to all these, I believe. But graph convolutional networks are kind of very similar to the message passing that we saw. And they basically aggregate features from neighboring nodes and keep aggregating that in iterations and pass through nonlinearity and then produce an embedding. And then there is so over here, the thing is you're sort of treating every neighbor of a particular node kind of uniformly. There are weights that you attach to the features, but you're not assigning specific importance to each node. Whereas graph attention networks do that a little bit differently, where in problems where you may see that, okay, one particular node may have more importance versus another node, and there are too many nodes in the graph, and then that's where graph attention networks can help zeroing in on specific nodes in the network and leveraging their features more, as opposed to just looking at all the nodes within the graph. Then there is Graph Sage, which is quite good for industry actually, because it makes GNNs work on large-scale graphs, and it primarily does that through sampling and aggregation. And so basically, it's not updating all the information from all the nodes, but it's sampling and updating. And that's sort of one of the main advantages of Graph Sage. The other advantage is so these don't necessarily extrapolate well to unseen data. For example, if there are graphs that have new nodes introduced into the graph, and the embedding has not been learned on that new node, Graph Sage would work better for such use cases. So what are some of the limitations here, right? I mean, graphs are not the one final super solution to everything. That's not what they are. But they do provide a very nice abstraction to solve certain problems that are probably hard to solve otherwise. So there are some, with this flexibility, there comes a little bit of some drawbacks as well, right? Scalability is one of them. So it is computationally expensive to process these on a large scale data. And then there are other challenges. For example, if the graph changes over time, or if the graph has different types of nodes where each node is not the same, they are completely different types of entities, different categories of entities, then that also adds to the challenges. And some of the emerging areas within graph neural networks is graph transformer networks, sort of making transformers. There's been some work on these fields, but I think more needs to be done So graph transformer networks is basically taking graphs and making them work with transformer networks. Spatiotemporal graphs, that one is actually something that I'm interested in. And it's basically looking at, let's say, data from various types of sensors from the human body, let's say, and there's a time component to it because you're monitoring those sensor data over time. And so there are multiple dimensions, and there's a time component to it. And then there's knowledge distillation, which is essentially making smaller models out of larger models. What are the key takeaways from this? As an applied ML scientist, or if you have, let's say, if you're in the industry and you have some data, one thing I would encourage is examine your data and see if you can model it as graphs. Because sometimes we have a lot of data and we are using them in certain ways, but there is more that could be done with that data. And but once you do that, also try to make sure if graphs are the most accurate representation of the system that you're analyzing. Because if it's not, if you can have a simpler abstraction for it, might as well just use that and not use graphs. But it's good to kind of think along those directions, because that can open up avenues for either extracting new types of insights or even building new products. And once this sort of intuition is understood from the data, it is also important to kind of see where the current state of the art of graph neural networks are, and whether they're suitable for the needs of solving that particular problem that you have at hand. And if you can leverage something that is already existing, maybe as a repository on GitHub or something of that sort, then that's great. If not, you may want to keep an eye out on the latest research that's happening in this field, because at some point in the future, it may become very relevant to your data. And as we look at the whole area, and we know there are scalability and optimization challenges, it's also important to sort of know and address that the scalability aspect of things. So that's pretty much concludes my talk. So here's a summary on of the talk, and I'll take questions. Thank you. Thank you.
A question about the Euclidean versus non-Euclidean.
Yeah.
Do you think that an undirected graph is also? I'm just curious to know how you visualize in your mind the fact that a graph is inherently non-Euclidean. Because in my head, I think about it as directionality. So the direction between two nodes going as you traverse a path from one end to the other is what makes a graph inherently non-Euclidean, as opposed to like an undirected graph where you could have gone 3 hops from one node to another node. So does direction play a role in that interpretation of non-Euclidean nature?
I think it's not just the direction thing, really. It's also about the fact that it's a completely different topology, and it's, for example, the concept of distance could be completely different. For example, if you're looking at, so what is the concept of distance in between nodes, let's say, right? It would probably be the weights that you add to the edges, and that you can add that up, and that would be the distance. And that paradigm, it just does not necessarily fit into a Euclidean space.
Yeah, but that's a very good point, because as you go from one node to another node,
yeah,
assuming that you have directions in one direction only, paths in one direction only for one type of node to another node, you can end up with a dead end, right?
Yeah.
So that's basically in my head what I think as non-Euclidean, because in a Euclidean space, you can go either direction. You're able to go forward and backward in space.
Whereas in a non-Euclidean space, the direction takes you to one part of the topology, but then you're trapped there because now the direction does not let you traverse in the opposite side direction.
That's actually not necessarily true. So, for example, if I were not to talk about graphs, but just non-Euclidean spaces or surfaces, a sphere is a non-Euclidean surface, and it's you could traverse in one direction and you can come back to the same place. So you'd not necessarily be trapped. The difference is that Euclidean spaces are the geometry of flat surfaces, whereas non-Euclidean spaces are the geometry of non-flat surfaces. So if you have curves and then everything changes, and let's say if you draw a triangle on a flat surface, the angles will add to 180 degrees. But if you draw a triangle on a sphere, it can be more than 180 degrees even, because you can. It's not really the triangle in the way that we imagine it, but in a non-Euclidean space, the sum of the degrees may not be 180, for example. Yeah. Yeah.
So you talked about relationships and nodes in the networks. I was just wondering, in your field of work, have you looked at networks from a higher level where you would consider centrality measures?
What measures? Sorry?
Centrality, like degree centrality, those kind of measures that look at the topology from above instead of like individual nodes within the graph.
No, not that I have seen. No.
Okay, thank you.
I'm not fully aware of the context of the.
Well, from my experience, it's mostly in HR systems where they look at the relationships between people and like the bottlenecks within the networks.
Okay.
Yeah.
So like higher degrees where more some nodes have higher degrees of connection versus other. So
yes,
the measures
yes.
of centrality.
Yes,
yeah.
exactly.
So we in my company we don't. The data that I have is more of the spatiotemporal nature. So it does not map very well to a social network or a type of data.
Okay.
Yeah.
Thank you so much.
Thank you. Hi.
I'll just bring a mic for you.
Yeah.
Thanks for waiting.
Hi, thank you. This is Razi. I have a comment and a question. The comments when you said when you are saving your graphs, you save information about the nodes and all of the information the nodes connected to that. I was thinking if you have a huge data set, it will be some kind of waste of memory because you are saving a data. For example, if it has lots of connected nodes, you're saving those information at the same time, and I think it's not more efficient and optimized. And my question is that if you have very huge data set and you have some information on the edge as well, like weights, but weights is not number. I work with number that the label is 0, 1, or -1, and 1, -1, 0. And if you have a huge data set that the labels are not number, for example, they are alphabet, how you save them very efficiently to use for machine learning models?
The question is, how do you save
a very huge data
more efficiently for
graphs that they are connected to each other and the edges has weights?
Right. So are you trying to like model this on your own, or are you using like a graph database for this? So because if you're because there are graph databases that would let you store information and query them in a more efficient way if you're handling large data sets.
Other than that, there is not any more efficient way because
as in if you're looking at let's say there are generally ways to compress a graph and store its information if the graphs are, let's say, sparse versus not, and they have different types of
the problem is that
edges. But if you're storing information in the node, then I think, and that's unique to a particular node, and then that information probably has to be stored. And
because some part of network is very dense, some part is sparse, and that's
Right, but if you still need to store a particular information for each node, you probably need to store that.
Okay.
So, yeah,
Okay. Thank you.
thank you.
All right, thank you.
Any other questions?
We're out of time.
Oh, okay, yeah, thank you. Thank you very much.